Okay, so we are going to talk a little bit about probability today. Specifically, we're going to talk about what's called conditional probabilities, and that's actually going to lead us right into what we call the multiplication rule. And then we're going to talk a little bit about independence. Here we go. So, if we know that something has happened, the probability of something else happening might change. And that's what we call conditional probability. So the probability that one event happens given that another event is known to have already happened. And think about notation here. This might be a new notation, that straight vertical line. That means the probability of B given A, or the probability of B on the condition that A has already happened. So we're going to just jump right into an example. In 1912, the Titanic struck an iceberg and sank. Some passengers got off the ship in lifeboats, but many died, as we know. So suppose that we randomly select one of the adult passengers from the Titanic. So we're going to define a couple events. F is that the person randomly selected was a first-class passenger. S is the event that the randomly select person survived. And T is the event that the randomly selected person was a third-class passenger. So we want to find the probability of T given S, right? Remember that vertical line means given then. So this is a conditional probability. And then we're going to interpret this value. So T given S, S is that someone survived. So we're saying, what's the probability that they are third class given that they survived? So in other words, I'm totally ignoring all of the people who died. And I'm also totally ignoring, therefore, like the total. So I'm only looking at those 442 people that survived. And so the probability that someone was a third class passenger, given that they survived, is 151 out of 442 people who survived. And your interpretation, basically kind of like I just said, given that the randomly chosen person survived, there was about a 34.2% chance that he or she was a third class passenger. You can also leave this as a decimal or as a fraction, and it does not matter. So that's your conditional probability. So you might be asked to find conditional probabilities like this, like using the notation, or you might be asked the question in words like in part B. So part B, given that the chosen passenger is not a first-class passenger, what's the probability that he or she survived? So you have to think about what's the given part. What's the part that we assume already happened? So we're assuming that the person is not a first-class passenger. So in this case, it's kind of like I'm ignoring these people, right? And I'm looking at either second or third class passengers. And so I'm looking at these people here in the yellow highlighted box. In terms of notation, remember being not first class, that's like a complement. So this would be the probability of S given F complement. And so out of those people in those yellow boxes, what's the probability that they survived, that someone survived? Well, then I would look at these people and I would take the 94 and the 151 people over the totals, those two totals, that 261 plus 627. So my probability would be about 27.6%. Okay, so let's do another example. You buy a bouquet of flowers for your Valentine. In it, there are 4 red roses, 2 pink roses, 3 red carnations, 3 pink carnations. And actually, before I even start this, let me mention this, that sometimes you're going to be calculating conditional probabilities from a two-way table, like this example we just did. And sometimes it might look like a problem like this, where it's not necessarily in a two-way table. So let's let event A to be the flowers are rose, and then event B to be that the flower is pink. So find the probability of A. Well, first of all, I need to figure out how many total flowers are there. So it looks like I have 12 total, right? 12 total flowers. And so the probability that the flower is a rose would be those 6 flowers out of 12, right? The probability that the flower is pink, this is event B, the probability of B would be the 2 pink roses and the 3 pink carnations. So it would be that 5 out of 12, these 5 right here. And then let's say, what's the probability, example number 3, what's the probability of A intersect B? Or in other words, what's the probability of A and B? So in other words, find me a flower that's a rose and it's also pink, right? So how about these 2 pink roses? There we go. How about those 2 pink roses? So that probability should be 2 out of 12, right? Now, let's look at those 1 through 3 are kind of like basic probability questions. Now let's look at 4 and 5. These are some conditional probabilities. So what's the probability of A given B? What's the probability, in other words, that you have a rose given that the flower is pink? So the given part in this case is that the flower was pink. So in other words, I'm only looking at the pink flowers. So now I don't have 12 total. I have 2 plus 3. So I have 5 total, right? And out of those 5 total, what's the probability that I have a rose? 2 out of 5, right? The 2 pink roses right here. Okay. And then number 5. So number 4, we're finding the probability of A given B. Now number 5, we want the probability of B given A. So this is something different. The probability of B given A, oh, I just put my answer up here already, sorry. The probability of B given A. So the given part is that the flower is a rose. So now I'm looking at these flowers that are roses. So now I have 6 of them. And what's the probability that one of those is pink? So that would be 2 out of those 6 roses. Okay, so we just calculated some conditional probabilities from this sample space. So basically I had a list, right, of all possible outcomes. I have like the sample space. So we're going to revisit these probabilities in a minute, and we'll talk more about that when we get there. But just to reiterate, we found these probabilities using this sample space. Okay, so let's look at this formula. So the probability of A given B is always going to be the probability of A and B divided by the probability of the given. So in this case, the given is B, right? So I'm dividing by the probability of the given. Now, I could ask you to find the probability of A given B, but I could also ask you to find the probability of B given A, right? So the probability of B given A is still the probability of B and A. And then remember, I'm always dividing by the given probability. And just to look really fast, the probability of A and B is the same exact thing as the probability of B and A. So that numerator would not change. But what would change is the denominator, what I'm dividing by. Because think about it. The given part is what I assume to have already happened. Okay. So we're going to revisit this problem now. And we are, instead of using the sample space, so now I'm going to kind of ignore the sample space. What if I didn't give you the sample space? What if I only gave you probability of A, probability of B, and the probability of A and B, right? So in number 4, I want to find the probability of A given B. So according to this formula, the probability of A given B would be the probability of A and B divided by the probability of the given, which is B. And so that would be 2 out of 12 divided by the probability of B, which is 5 over 12. 2 over 12 divided by 5 over 12. When I divide, I can multiply by the reciprocal, right? That's 2/5. Whoops. 2/5. And if I go back 2 pages, remember, we got 2/5 to begin with from our sample space. So my point is, it doesn't matter if I use the sample space to calculate a conditional probability or if I use this formula. It's whatever I'm given. I can use whatever I'm given to calculate these probabilities. And then number 5, the probability of B given A would be the probability of B and A over the probability of A now, right? The probability of B and A is still 2 out of 12. The probability of A now was 6 out of 12, right? And again, I am not looking up here at all. I'm just looking at these probabilities. So I know 2 out of 12 times 12 over 6 is going to be 2 over 6, or 1/3. And if I go back, we got 2 out of 6 from the sample space as well. Okay, so either method, using the sample space, you need to be able to do. You also need to be able to use the formula. All right. Let's look at another problem. You need to be able to do problems like this. A survey of all residents in a large apartment complex reveals that 68% use Facebook, 28% use Instagram, and 25% do both. So suppose we select a resident at random. Given that the person uses Facebook, what's the probability that she or he uses Instagram? So before I do anything, you might want to even say to yourself, okay, the probability that someone uses Facebook, 0.68, right? The probability that someone uses Instagram, 0.28. What's this 25%? 25% do both. Well, that's F and I, or F intersect I, right? So what's the given that the person uses Facebook, what's the probability that she or he uses Instagram? So that's the probability of I and F divided by the given. What's the given? Facebook. So that probability would be 36.8%, or 0.368. Okay, so I have a problem for you to think about. About 55% of high school students participate in a school athletic team, okay? So roughly 6% of these athletes go on to play on a college team in the NCAA. What percent of high school students play a sport in high school and go on to play on a college team or NCAA team? So I can let you think about this for a minute. And you'd probably say, oh, well, I want to figure out, well, what's 6% of 55%, right? So 6% of 55, I know I can multiply 0.06 times 0.55. And I get 3.3%. So about 3.3% of all high school students would play the sport in high school and then go to play in college. That's just kind of like intuitive. Like we've kind of known how to do that for a long time. But let's talk about why we can do that. Why can we multiply those two percentages together? So let's take this formula that we just used, and we're just going to do some algebra with it, right? This is the conditional probability formula. We're going to multiply both sides by the probability of B. So I now get the probability of B times the probability of A given B, so times the conditional, is equal to the probability of A and B. And that brings us to our next important rule that I told you about we were going to learn, which is what we call the general multiplication rule. And this is always true. If I want to find the probability of A and B, I can take the probability of A and multiply by the probability of B given A. Or I can take the probability of B and multiply by the probability of A given B. So these two things are equivalent. You could say like the probability of A times the probability of B given A is going to be the same as the probability of B times the probability of A given B. Okay? All right. So let's revisit that problem we just looked at. 55% of high school students participate in a school athletic team. 6% of those athletes go on to play in a college team. So what percent of high school students play a sport in high school and go on to play on an NCAA team? So what we did was we multiplied that 0.55 times the 0.06. We were like, oh, we just need 6% of 55%, right? Let's talk about what those things really were. That 55% is just the probability that someone plays a high school sport. And then it says 6% of these athletes, or in other words, 6% of the high school athletes, right? So let's call this like H, that they play in high school. And let's call N that they play in the NCAA, right? So 6% of those high school athletes go on to play in the NCAA. So in other words, that's the probability that they go on to play in the NCAA given that they played in high school. That's this part here. And we multiplied those two together to get that 0.033 or 3.3%. So without even realizing it, you've always kind of, or I shouldn't say always, but for a long time, you've known a little bit about conditional probabilities and using them to some extent. Okay, so just that same rule again. Let's use it. So the Pew Internet and American Life Project reported that 79% of teenagers use social media and that 39% of teens who use social media feel pressure to post content that will be popular and get lots of comments or likes. So I need to think about what's going on here before I answer any type of question. It says in that first sentence, 79% of teenagers use social media, right? 39% of teens who use social media feel pressure. So that 39%, this is a conditional probability. The 79% is not. So let's find the probability that a randomly selected teen uses social media and feels pressure to post content that will be popular and get lots of comments and likes. So let's see what we have. That 39%, that's the probability that someone feels pressure given that they use social media. And that 79% was just the probability that someone uses social media, right? So if I multiply these together, I will get the probability that someone uses social media and feels pressure. So just to reiterate, we'll call this A and we'll call this like B given A. So it's the probability of A times the probability of B given A. You're multiplying by whatever the given part is. If the conditional is A, then I'm multiplying over here by the probability of A. When the conditional was B, so if it was probability of A given B, then I'm multiplying by the probability of B. Okay? All right. Another quick one. Miss Chang's kids have a lot of stuffed animals. If you randomly pick a stuffed animal, the probability that it's gray is 35%. The probability of a stuffed animal being an elephant, given that the animal is gray, is 0.2. What's the probability of randomly picking an animal and getting a gray elephant? So actually, I underlined this and I really don't need to. The gray elephant means, like I'll call G the animal being gray, and I'll call E the animal being an elephant, right? So what am I given? I'm just given the probability of G equals 0.35. And then this 0.2, what is it? It says the probability of a stuffed animal being an elephant given that the animal is gray. So the probability of being an elephant given that the animal is gray, that's 0.2. So now it's saying what's the probability of randomly picking an animal and getting a gray elephant? That's the intersection of G and E. So I want the probability of G and E. So I can multiply that 0.35 times that 0.2. And I get 0.07. Okay. Let's talk about independence. So A and B are independent events. If knowing whether or not one event has occurred does not change the probability that the other event will happen. So a couple questions for you. Is the weather in Ambler independent of the weather in Upper Dublin? So in other words, if I know it's snowing in Upper Dublin, does that tell me something about what's happening in Ambler? Now, these two towns are right next to each other, right? If it's snowing in Upper Dublin, it doesn't guarantee that it's snowing in Ambler, but I would say that if I know it's snowing in Upper Dublin, the chances that it's snowing in Ambler are probably higher than if I didn't know anything about what's happening in Upper Dublin. So I would say, no, they're not independent, right? They're dependent on one another. Now, is the weather in Ambler, Pennsylvania, independent of the weather in Australia? This one I think is a little tricky because honestly, I would probably say no. But I have had students say to me, well, Mrs. Chang, the weather is like global. What happens in Australia impacts what happens in Ambler. Maybe not that day, and vice versa. Maybe not that day, but a week later or whatever it is. So maybe they're not independent. I'm kind of unsure. Is the number of points that the Eagles score in one game independent of the number of points that they scored the game before? So we're talking about number of points. We're not talking about like whether they win or lose. So again, I would probably want to say that they are independent, but anyone who knows about sports and injuries and things like that, just like mentalities, you're on a high, you're on a low, they're probably not totally independent. I don't know for sure that they are, right? How about this one? When I roll a die twice, is the outcome on the second roll independent of the outcome on the first roll? So if I get a 5 on the first roll, does that change the probability that the next roll I get a 2? Nope. No matter what happens on the first roll, the probability of getting a 1 is still a 1/6. The probability of getting a 2 is still a 1/6, et cetera, et cetera. So just a quick recap. Are these independent? Probably not. These are probably like a maybe, questionable, and this is a definite yes. So when we talk about independence in statistics, it's either a yes or a no. There is no maybe. So if it's a maybe, guess what? It's a no. The answer is no. They can only be independent if they are truly independent mathematically. Like you might have heard me just say, if I roll a 5, what's the probability of getting a 1 on the second roll? It's still 1/6. It didn't change the probability that the next event is going to happen. Okay? All right. So that brings us to our definition of independent events. So A and B are independent events if knowing whether or not one event has occurred does not change the probability that the other event will happen. In other words, think about this formula. A and B are independent if, and I want you to kind of ignore this for a second. Just think about this. The probability of A given B is equal to the probability of A. In other words, it doesn't matter whether it doesn't matter whether B has happened or not. And that brings us to this B complement thing here. So whether B happened or whether B didn't happen, the probability of A is always the same. Alternatively, if A and B are independent, then if I know that A happened, or if I know that A didn't happen, the probability of B is always the same. So to be clear, if A and B are independent, all of this has to be true. So basically I have like 4 truths. If A and B are independent, probability of A given B has to be equal to the probability of A. The probability of A given B complement has to be equal to the probability of A. The probability of B given A has to be equal to the probability of B. And the probability of B given A complement has to be equal to the probability of B. So if A and B are independent, all 4 of those things are true. Okay? Let's look at this two-way table and some data about gender versus whether or not people have their ears pierced. And let's think, are these 2 variables independent or not? So if I look at this conditional probability, because it's all about the conditional probabilities, the probability that someone has a pierced ear given that they're male is 19 out of 90, or 0.211. The probability that someone has a pierced ear given that they're female is, so in other words, like not A complement, is 84 out of 88, 95%. These 2 percentages are very, very different. And then let me find, before I put that up, let me find the probability that someone has just a pierced ear. So in other words, the probability of B. So the probability that someone having a pierced ear would just be 103 divided by 178, which is what? What's that? 103. 103 divided by 178. So 0.5, we'll make that 0.58. Okay? So the probability of someone having a pierced ear is 58%. If these events were independent, when I found this conditional probability, this should be 58% and this should also be 58%. They would all be exactly the same. No rounding, exactly the same. So because they're very different, they're not independent. Thinking about this, knowing that a student is male greatly reduces the probability that the student has a pierced ear. Or you could think, if I just consider, what was the probability just that someone had a pierced ear? Now I forget. Oh my gosh. Hold on, I deleted it. So the probability that someone had a pierced ear was just 58%, right? But then I'm like, well, wait, I know that they're a girl. Oh, well, then it's a much higher chance that they have a pierced ear. It goes up from 58% to 95%. So because that probability changed, the events are not independent. Okay. So that brings us to another example. Is there a relationship between gender and handedness? So whether you're like your dominant hand is right-handed or left-handed. To find out, we use Census at Schools random data selector to choose an SRS of 100 Australian high school students who completed a survey. Notice it's an SRS. So the two-way table summarizes the relationship between gender and dominant hand for these students. Suppose we chose one of the students in the sample at random. Are the events male and left-handed independent? Justify your answer. So remember, if you're asked this question, I don't care what you think. You might say, oh yeah, it doesn't matter, like off the top of your head. It doesn't matter if you're a male or a female. You know, your dominant hand wouldn't matter. That's not what we're asking here. Because what you think might be very different than what we see in the data. So what does the data show us? So we're going to be looking at conditional probabilities. So what's the probability that someone's left-handed given that they're male? So in other words, if I just look at the males, the probability that someone's left-handed is 7 out of 46. The probability that someone's left-handed given that they're female is 3 out of 54. These two probabilities are very different. And I could have also said, what's the probability just that someone's left-handed would be 10 out of 100, or in other words, 10%. So none of these are equal to 10%. So therefore, these two events being male and left-handed are not independent. Knowing that the student is male actually increases the probability that the student's left-handed. Okay. Let's do another example. So far, we just talked about independence from a two-way table. So what about this? If you flip 2 coins, list the sample space. So what can I get? Heads, 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 tails, tails, heads, or tails, tails, right? Oh, sorry, excuse me. Okay, so let's define event A to be that the first flip is heads, and event B is the second flip is tails. So are these two events independent? Let's check. Again, I don't care what you think, right? We're going to do this mathematically. So find the probability of A. So the probability of A would be from the sample space, the first flip is heads would be the first two possible outcomes, right? So outcome 1 and outcome 2. So it would be 2 out of 4, or in other words, a half. Find the probability of B that the second flip is tails. It would be the second outcome and the fourth outcome, right? So 2 out of possible 4 outcomes, or in other words, 1/2. So find the probability of A given B using your sample space and the definition of theoretical probability. So A given B. So remember, given that the second flip is tails. So I'm only looking where that second flip is tails. What's the probability of A given B? What's the probability that the first flip is heads? It would be 1/2, right? So now find the probability of A given B using the formula. So remember, conditional probability, my conditional probability, I'll try and squeeze this in, would be the probability of A and B divided by the probability of the given part. What's the probability of A and B from the sample space, the first flip being heads and the second flip being tails? Well, that's this one right here, right? That only happens 1 time out of 4 possible outcomes, right? So the probability of A and B would be 1/4 divided by the probability of B, which is 1, I'll do 2/4. So in other words, 1/4 times 4/2, or in other words, 1/2. So same answer, whether I use the sample space or whether I use the formula. Just a reminder, you can do the same thing 2 different ways. Okay, so let's compare now the probability of A to the probability of A given B. So I can now say the probability of A is equal to the probability of A given B. 1/2 is equal to 1/2. Check, right? But now let's look at the probability of B given A. B given A using my sample space. So now the given part, let me go green here. So I'll highlight this green. B given A. So if the given is that the first flip is heads, that's either this or this, right? So now what's the probability that the second flip is tails? Again, No. Sorry. Here, hold on. Here we go. Okay. So find the probability of B given A using our sample space. So again, we highlighted these things in green because the first flip being heads are those two ones in green. So what's the probability now that the second flip was tails? It's this one here. So it happens 1 out of 2 times, or in other words, 1/2 of the time. Now using our formula, we need the probability of A and B divided by the probability of A now, because A is the given part. So the probability of A and B, remember, was 1/4. The probability of the given was 1/2, or I'll make it 2/4. It'll be easier for me to do the math here. So 1/4 times 4/2 is 1/2, right? So now I know if I go back and look at the probability of B, the probability of B is equal to the probability of B given A. 1/2 equals 1/2. So remember, we said there's basically like 4 things that need to be true. Here's one thing that needs to be true. Here's the second thing that needs to be true. The third thing that needs to be true is that A given B complement has to be equal to the probability of A, and B given A complement has to be equal to the probability of B. Well, let's just quickly use the sample space. A given B complement. So B complement, B is the second flip is tails, so B complement would be the second flip is heads, right? I'll use pink. So if the second flip is heads, that's this and this. Now, what's the probability that the first flip is heads? That's 1/2. So now check, that's equal to the probability of A. And then last but not least, this is getting very colorful. The probability of B given A complement. A complement would be that the first flip is not heads, so the first flip is tails. That's this and this, right? So what's the probability of B that the second flip is tails? 1 out of those 2 possible blue outcomes. So this is 3, and then this would be 4, because the probability of B is equal to the probability of B given A complement. And the probability of A is the probability of A given B complement, right? So we have now just proved that flipping 2 coins and having the first flip be a heads and the second flip being the tails, we have proved mathematically that they're independent. So from here on out, if I ask you that are 2 events independent, you're not just going to tell me, oh yeah, because the first one doesn't affect the second one. No. You have to show me mathematically that the first one doesn't affect the second one. Okay. All right, so we know that this is true now. The probability of B given A is equal to the probability of B if A and B are independent. So watch what we can do. So if 2 events are independent, the probability of B given A is really the probability of just B. And so therefore, again, if A and B are independent, the probability of A and B is just equal to the probability of A times the probability of B. Now, this brings me back to like basic probability that you learned middle school, maybe even younger. But I always teach my younger students, like when it says, what's the probability of A or B, you add. What's the probability of A and B, you multiply. But now here we are, and we're learning a little bit more that it's not just that simple. A or B, you add only if the events are disjoint, right? The probability of A and B, you multiply only if the events are independent. If they're not independent, you have to multiply A times the conditional probability, right? Okay, so this new formula is only true for independent events. Okay, so same kind of problem that we did before. Heads, 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 tails, tails, heads, tails, tails. That's your sample space, right? We're doing the same thing as before, defining A to be the first flip is heads, B the second flip is tails. So to find the probability of A, the first flip being heads is 2 out of 4. Find the probability of B, the second flip being tails is again 2 out of 4, right? Find the probability of A and B using your sample space and the definition of theoretical probability. So watch. A and B, meaning find me the flip that has the first flip heads and the second flip tails. That's this one, right? So the probability of A and B is 1 out of 4. This is not a conditional probability. Now, find the probability of A and B using the rule above. Because I proved a couple minutes ago, I proved that A and B are independent. If I want the probability of A and B, I can just take the probability of A and multiply by the probability of B. Again, I know you're tired of hearing me saying it, but I can only do this because they're independent. So the probability of A was, let me reduce these to make it easy. The probability of A was 1/2. The probability of B was 1/2. So the probability of A and B is 1/4. So I can find the same probability from my sample space or using the formula. And you're going to notice, I'm going to say this over and over. We can use the formula. We can also use the sample space. And believe it or not, I know students don't want to hear this a lot of times, but I really think that using the sample space sometimes is easier than using the formulas because I strongly believe that the formulas are often misused. Okay. Let's try one more practice problem. So an interesting one. Many people who visit clinics to be tested for HIV, the virus that causes AIDS, don't come back to learn their test results. Clinics now use rapid HIV tests that give a result while the client waits. So same thing with rapid COVID tests, rapid flu tests, rapid strep tests. If you've ever had one of these tests, if you've been sick, you probably know that they do the rapid test and then they also send away the actual, I don't know what it would be called, but like the test that takes a couple days to come back. And that's because what we're about to read, ready? So in a clinic in Malawi, for example, use of rapid tests increased the percentage of clients who learn their test results from 69% to over 99%. The trade-off for fast results is that rapid tests are less accurate than the slower lab tests. Applied to people who have no HIV antibodies, one rapid test has a probability of about 0.004 of producing a false positive. So think about it. I'm going in to take this rapid test and I don't actually have HIV. I don't, right? But the test is showing me that I do. How often does that happen? It's not very often. It's less than 1% of the time, right? It's less than 0.5% of the time. But it happens. So if a clinic tests 200 randomly selected people who are free of antibodies, what is the probability that at least one false positive will occur? And now here, this is big. Assume that the test results for different individuals are independent. If they weren't independent, then I really wouldn't be able to do what I'm about to do. And so what does that mean in real life? The test results are independent, meaning like if I'm a couple in a relationship or if it's like a mother and child, those results are probably not going to be independent, right? Just food for thought. So anyway, what we can do is basically we're going to use the complement rule. If I want the probability that at least one, hold on, before I go here. If I want the probability that at least one false positive will occur, that's really the probability that we have one false positive or the probability that I have two false positive, and these are independent. So plus the probability that I have 3 false positive, plus 4, plus 5, plus 6, all the way up to 200. This would take me forever to figure it out. So I'm going to use the complement rule. So this is going to be if I want the probability that at least one false positive will occur, I can figure out, well, what's the probability that no false positives occur? And then I can do 1 minus that. So keep that in mind. That's our goal. So the probability for no false positives would be, in other words, that all 200 tests were negative, right? And again, we're saying that we're assuming that all 200 people were free of HIV. So all 200 people are free of HIV. So we have a probability of 0.004 of producing a positive given that you're free of HIV. So 1 minus that, 0.996, would be the probability of me going in without HIV and getting a test result that says I don't have HIV, right? So basically getting the correct test result. So it would be 0.996 to the 200th power. So 0.4486. So the probability of no false positives is 0.4486. So therefore the probability of at least one false positive would be 1 minus that, which would be 55.14%. So think about it. There's a good chance, a very, very good chance that if I test 200 people who don't have HIV, I'm going to have at least one false positive. That means there's a lot of false positives. When I say a lot, I mean like a relatively a lot, right? All right, that is the end of it. Thank you so much for listening and watching, and have a great day.